Chapter 18, Example 1. The National Center for Education Statistics monitors many aspects of elementary and secondary education worldwide. Their 1996 numbers are often used as a baseline to assess changes. In 1996, 34% of students had not been absent from school even once during the previous month. In the 2000 survey, responses from 8,302 randomly selected students showed that this figure had slipped to 33%. Officials would, of course, be concerned if student attendance were declining. Do these figures give evidence of a change in student attendance? So we're going to test something. We want to say, has it changed from the 34% rate? So we make a hypothesis. Our null hypothesis, H naught, will be that the probability has stayed the same. P equals 0.34. Our alternative, since we just want to know do they give evidence of a change, will be that the probability does not equal 0.34. So we can talk about it's increased or decreased. So HA probability does not equal 0.34. That's step 1. Step 2, check your conditions. We have a random selection of students and 8,302 students are less than 10% of all U.S. students. I would expect 2,822.68 students that had not been absent in the past month. And 5,479.32 students that had. Both at least 10. I can use the normal model for a 1 proportion Z test. So now we're not doing an interval, we're doing an actual test because we're testing that hypothesis. That was step 2. Now we're going to look at some statistics, calculate a standard deviation, a z-score, and move on to our final conclusion. So n equals 8,302. So our standard deviation of p, we're doing it for the baseline value, not our sample value. So standard deviation of p, we're using standard deviation, not standard error, equals 0.34 times 0.66. So we're using the population parameter, what we believe the true value is, divided by the sample size, 8,302, which equals 0.0052. So in a test, a z-test, you're always checking the baseline value. Our normal model will be n equals 0.34, 0.0052. So we can look at our normal curve real quick. We want to say, is that value of 0.33 unusual? And so we're doing it on both sides because we're just saying it's not equal to 0.34. So we kind of know how far the 0.33 is on the left side, mirror it on the other. Our z-score will be z equals 0.33 minus 0.34 over the standard deviation we just calculated of 0.0052. This gives us a z-score of negative 1.92. To calculate our p-value, which is what we use to actually assess the probability here, is 2 times, since we're doing a two-tailed test, 2 times the probability that z is less than negative 1.92. So we look that value up in the table, the negative 1.92, and we double it. And we get 0.0548. That is called our p-value. Usually we go from a benchmark of like 0.05. If it's above 0.05, we consider it high. If it's below that, it's low. So my p-value of 0.0548 is not that low, and I will fail to reject the null hypothesis. There is not sufficient evidence to indicate the absence rate has increased since 1993. Now, the thing is, with a 0.0548, you could say, oh, that is still pretty low. I think there is evidence. Especially if you looked at a one-tailed test, if we just look below 0.34, it definitely would be low. So there's some wiggle room here for sure. It's the statistics that we're really worried about.